Hello everyone, this is your next research methods lesson on probability, so make sure you have your notes and your pen ready. So just to get you thinking, I want you to picture that I've got a deck of cards in front of you and I ask you to just pick one, and we're just going to get you thinking about probability of picking certain cards. So bearing in mind there's 54 cards in a deck, 13 of each suit. What is the probability that if I pick one card, it will be from a red suit? So pause me and have a think about it. What's the probability? It could either be a fraction or a percentage. So it's 1 out of 2 or 50% chance that you would pick a red one, obviously because there's 2 black suits, 2 red suits. What is the probability that if I pick one card, it will be a picture card? So consider each suit has 13 cards and there are 3 picture cards in each suit. So therefore it would be 3 out of 13, or you might have worked out the percentage, which is 23%, to 2 significant figures. Number 3, what is the probability that if I pick one card, it will be an even number? So not counting the jack, the queen and the king. This would be 5 out of 13 or 38%. Probability is something that we think about all the time. Probability is all about chance. What is the likelihood that something is going to occur by chance? So what if I asked you, would you like to buy a £50 raffle ticket to win this car? You would probably be asking, okay, well, how many people can buy raffle tickets? How many raffle tickets are there? If there are 10, say, being sold, do you want one? Your answer is probably going to be yes, because the chance of you actually winning the car is very high, and because you have 1 in 10 chance of being chosen. What about if there was 1,000 tickets being sold? Then you probably wouldn't want to spend £50 on risking that. So how probable is it that you would win if 1,000 tickets are sold? I want you to work out the percentage for that. So you should have got 1 in 1,000 or 0.1% compared to if there was only 10 raffle tickets being sold, which would be 1 in 10 chance, or 10%, which is quite a high chance. We see statistics all the time in the news and in the media. So say you saw a headline that says statistics show women are better than men at reading maps. How do you think this was tested? They obviously haven't tested every single woman and every single man in the whole world at reading maps. So what they've done is they've taken a sample, and that sample is representative of the wider population, or it should be. And if women are indeed better than men, then we can infer that the same is true for all women and men. And this is where the term inferential statistics come from, because if we do a statistical test, a statistical analysis on our data, then we can infer that the data collected from our study is also true for all men and women. We can only make such inferences by using inferential tests based on probabilities, and this is where we talk about p is less than or equal to 0.05, but we'll talk about that a little bit later on. What does the term falsifiability mean? We looked at this when we did the features of a science, so I want you to pause me and try and write a definition of what falsifiability is. Falsifiability means being able to prove a hypothesis wrong. So it's a key feature of a scientific theory, because if something cannot be falsified, if something cannot be proven wrong, such as Freud's psychoanalysis, then it's seen as less scientific. We want to investigate whether men and women are the same in terms of their map reading abilities. What would be a null hypothesis for this? I want you to write down the null hypothesis. So you should have written something along the lines of, there is no difference between men and women in terms of map reading ability. Okay, null hypothesis always states that there is no difference between the two IVs, the IV here being the men and the women. So to test our aim, are women better at reading maps than men? We need to falsify this null hypothesis. We need to prove it wrong. So we go off and we collect our data from 20 men, 20 women. That's our sample. And the question we seek to answer is, what is the probability that the data collected came from a population where men and women have the same map reading abilities? In other words, is the null hypothesis correct? And if it's not correct, we can reject that and accept that that women are better at reading maps than men, or we could find the opposite is also true. Men are better at reading maps. Okay, so an example now of probability, and it was done by Kulikan in 2004. And basically, he was convinced that his local fish and chip shop saved money by giving some people thinner chips. So you get more chips for each potato if you make the chips thinner. So therefore, you're saving money. There were 2 chip bins under the counter. So he asked for chips from each. He went home and he measured the widths of chips in each bag. So obviously had a lot of time on his hands. Belief 1, we can look at it as the 2 bins contain chips of equal width. And belief 2, we can look at being 1 bin contains chips thinner on average than the other. After he measured them, he found a very small difference between the average width between the 2 bins. We would expect a little difference in anything because things vary all the time. It's called random variation or chance. But what we're looking at when we do scientific research is a sufficiently large difference between the samples to make sure that the bins or the total population are actually different. And this is where statistical tests come in. Otherwise, if the difference isn't large enough, then we must assume that the populations, or in this example, the bins, are the same and the chip widths are the same. Let's compare this chip example to the earlier example we were talking about before with the map reading abilities of men and women. So in this case, in the chip example, the bins were the populations. So one population was the fat chips, one population was the thinner chips. And the populations earlier were the men and the women. Kulikan didn't measure every single chip from each bin. What he did is he took a sample from each bin, just as we did with the 20 men and the 20 women. The belief that there are 2 bins of containers of the same width chips is the null hypothesis. In other words, there is no difference between the widths of the chips between bin 1 and bin 2. Just as earlier we stated the null hypothesis for the map reading, as there is no difference in map reading ability between men and women. The alternative belief that 1 bin has thinner chips is an alternative hypothesis. So that's stating that there is a difference. So it could be directional, so saying bin 1 contains bigger chips than bin 2, or it could be non-directional, and you can just state that there is a difference. There is a difference in width of chips between bin 1 and bin 2. And in our earlier map reading example, I want you to try and write an alternative hypothesis for the map reading example. So give me a directional one, tell me which way the results are going to go, and then give me a non-directional one, just telling me that there's going to be a difference between the 2 samples. So you should have written something like, for the directional one, you should have written women will perform significantly better at reading maps than men, or their ability will be higher than men's, words to that effect. And for the non-directional, you would have written there will be a difference in map reading ability between men and women. So remember, you'd have to state both of your IVs, both of your samples. So let's stop talking about chips now, because some drama has occurred. You were walking through school and you stumbled across the projection room above the auditorium. Shout out Mean Girls fans. And you see this. So you're pretty sure they were kissing, but you're not 100% sure. So obviously you ask yourself, how likely is it that Regina would be kissing Shane if nothing was going on between them? So as a scientist, your natural reaction would obviously be to get some hypothesis going. So you'd start with your null hypothesis. There is nothing going on. There is no relationship between them. But then your alternative hypothesis is telling you there is something going on between them. So based on the evidence, which hypothesis do you reject? And in this case, I mean, it looks pretty dodgy. So I think you would probably reject the null hypothesis that there is nothing going on between them and there is no relationship. So you go and you tell your mate, Aaron Samuels, that Regina is cheating on him. But in research, we need to be more precise than fairly certain. We can't just be fairly certain that something has happened, because it could be due to chance, that something else could explain that difference. In order to work out whether there is a difference, whether the difference is significant, so in other words, whether the difference is big enough, we use a statistical test. And these allow us to work out how probable it is that a pattern in research data could have arisen by chance, so it just happened, or because of a real difference in the population from which a sample was drawn. However, you can never be 100% certain that an observed effect was due to chance, but you can state how certain you are, and this is where P comes in. So, for example, in the Mean Girls example, you might say that you might tell Aaron Samuels that you are 99% sure Regina is cheating. So that's fairly sure, but it's leaving that 1% of uncertainty. When testing hypotheses, we usually use a probability level of 95%. So you need to be 95% sure that something occurred not due to chance. That there's a real difference between the sets of data, and it's not just a chance. This expresses the degree of uncertainty. It means that there is a 5% chance or probability of the results occurring if the null hypothesis is true. So even if there was nothing going on, there's a 5% chance that that would have still happened. In other words, a 5% probability of the results would occur even if there was no real difference, correlation between the populations the sample were from. So in the map reading example, we want to be 95% sure that the differences between map reading abilities in men and women are no less than 5% due to chance. And this is recorded as P is less than or equal to 0.05. In other words, the chance, so the probability of it occurring by chance is 5% or less. And you're 95% sure that there is a real difference between them. Why might some studies want to have a significance level of P equals less than or equal to 0.01? I'm going to pause me and have a think about that. So this significance level isn't always easy to get. However, when replicating a previous study, so we're fairly certain how the results are going to go, we might want to reduce the significance level to 0.01 just to be extra sure that there is a difference between our data. Or when considering the effects of a new drug on health, because you don't want it to be due to chance, you want to know that the drug is making a real difference, and 5% chance of it occurring, 5% probability of it occurring by chance is probably a little too high for drug trials. Type 1 and type errors can happen in any given research. Type 1 errors is when we reject a null hypothesis that is actually true. So we say that there is a difference when there isn't a difference. So how could this relate to the map reading example? The map reading example, we would say that there is a difference in the ability of men and women to read maps when there is no difference, because the null hypothesis is true, there is no difference, but we've rejected that and we've accepted the alternative hypothesis that there is a difference in the ability of men and women. And then we have the opposite, which is type 2 error, and this is when we accept a null hypothesis that is actually false. So how would this relate to the map reading example? We would say that there is no difference in the ability of men and women to read maps when women are better or men are better. So there is a difference between men and women, but we've accepted a null hypothesis that there is no difference, but that is false. A significance level of 5% provides the best balance of type 1 and type 2 risks. So some researchers do decide to use a significance level of 10%, but that makes it more likely that type 1 and type 2 errors will exist. This is a good way to try and remember what causes type 1 and type 2 errors. So up here we have the truth, which we will never truly know, but we can be fairly certain if we use a significance level of 5%. And in the first case, the null hypothesis is true. So we have found with our data that there is no significant difference between the two groups. However, we have rejected the null hypothesis, and this has created a type 1 error because the null hypothesis is true, but we've rejected it and we've said that there is a difference when there's not. And then in the type 2 column, we have it's this time the alternate hypothesis is true. So there is a difference between men and women in the ability to read maps, but we've accepted the null hypothesis. So we've said that there is no difference, and this is what has created a type 2 error. Just to finish off, I want you to answer these next 9 questions. The first 3, I want you to write a suitably operationalized null hypothesis and directional alternative hypothesis. Remember, directional will tell us the way that the results are going to go. It's telling us the direction that they're going in. By operationalized, I mean to make it specific and measurable. So you need to specifically tell me what the 2 IVs are, what are your 2 conditions, and what is the DV, what are we measuring? Number 1, an investigation to see if people who regularly watch football are better at remembering a set of football scores than people who never watch football. What would a null hypothesis for this be? And what would a directional alternative hypothesis be? Number 2, an investigation to see if people farming in Wales or England suffer more symptoms of stress. What would the null hypothesis be? What would directional alternative hypothesis be? Think about what DV would be here. What are we measuring specifically? And number 3, an investigation into the relationship between alcohol consumed per month and work absence. So again, I want you to write me a HO, so a null hypothesis, and a H1, directional alternative hypothesis. So pause me now, the answers are on the next slide. So a null hypothesis for this would be there is no difference between the number of sets of football scores. Remember, this is operationalized because it's mentioned the word scores, recalled by people who watch football weekly, very specific IV1, and those who do not watch it at all, again, specific IV2. An alternative hypothesis would say people who watch football on a weekly basis remember more sets of football scores than those who do not watch at all. So it's told us the way the data set is going to go by using the word more. The second one, a null hypothesis, there is no difference in the scores of farmers from England or Wales on a stress symptom inventory. So again, it's made it measurable and specific. We know exactly how we're measuring stress. You might have said stress score or either the stress symptom inventory or stress score is probably what you've written. The alternative hypothesis, the scores of farmers from England are higher on a stress symptom inventory than the scores for farmers in Wales. Now, it doesn't matter which IV you've put where. You might have said that the scores for farmers in Wales will be higher than the ones in England, but that is still directional because it's telling us which way it's going to go. An investigation into the alcohol and work absence. There is no relationship between the number of alcohol units consumed in a month and the number of absence days from work. Look how operationalized that is in terms of alcohol units consumed in a month. So it's given us a specific time frame as well, and the number of absence days. So it's very measurable, very specific. The more alcohol units consumed in a month, the greater the number of absence days from work. Or you could have written it as those who consume more alcohol units in a month will have a greater number of absence days from work than those who consume less. The final 6 questions now, and these are all on hypotheses and significance. What is another term for a one-tailed hypothesis? Think about the cat who only has one tail compared to the cat who has 2 tails. Hopefully that makes sense if you remember that lesson. 5, when would you use a one-tailed hypothesis? 6, what is the usual level of significance employed in psychology? I want you to write it as a decimal and a percentage. Number 7, justify why psychologists use the level stated above. Why is it the best level to use? What is a type 1 error? What is a type 2 error? So pause me now and then review your answers on the next slide. Another term for a one-tailed hypothesis is a directional hypothesis. So a cat who only has one tail, we know which way they're going to be walking. We know which way the results are going to go. However, if a cat has 2 tails, we're not sure. It's non-directional. We're not sure which way it's going to walk. When would you use a one-tailed hypothesis? You would use this when we've seen previous research on it and it's fairly consistent in establishing the direction of the results, or if it's just common sense. What is the usual level of significance? It's 0.05 and 5%. And justify why psychologists use this level stated above. It provides the best balance of type 1 and type 2 risks. What is a type 1 error? It's rejecting the null hypothesis when it is true and we should have accepted it. A type 2 error is when we accept the null hypothesis when in fact it's false and we should have accepted the alternative hypothesis because there is a difference in the data sets. Okay, so that's all for this lesson. As always, post your notes onto Teams. Any questions, let me know. Thank you.